All right, hi there. So in this video, I'm going to kind of go one step deeper into what I discussed in a previous YouTube video, an auxiliary video that I made titled, I think I titled it Dividing by Zero Twice. So in that YouTube video, I introduced a vector field right here. I've copied it right there. It's certainly a mess, but there is lots of division, lots of denominators, and there are two discrete locations where these denominators equal 0. So 2 spots where the denominator is 0, 2 spots that I cannot put into the vector field, so the domain is all real numbers minus those 2 locations. Okay, but there is a really interesting property that I have to say about this vector field. There's a reason why I picked the 2 locations. I could have picked the 2 singular locations to be anywhere, but the fact that they are so symmetric about the x equals 0 line sort of has some nice implications. Okay, so I want to take a pause and just say, suppose you have any vector field V is PQ on the plane. Now, suppose you have the following symmetric properties where P of negative x comma y equals negative P of xy, and Q of negative xy equals Q of xy. You can check in the above case that this is the case that we're in. So this has a very special symmetric property. The reason why is if you actually look at the vector field, we've got these singular loci, I don't know how to say that word, L-O-C-I, loci, I feel like I should know this. Anyway, the vector field looks like this. There's some sort of symmetry about the line, about that vertical middle line that I'll bold in red right here. If you were to fold both sides in, smack them on top of each other as if it was a painted illustration in wet paint on both half pages, they would slap onto the same picture as you folded them onto the middle. So that's the picture that we see right now, that the left side is sort of some sort of flipped version of the right side. Okay, and that is reflected by the algebraic equations right here. So what I want to say is that anytime you're in this situation, you can actually exhibit some sort of 180-degree rotational symmetry about that vertical line x equals 0. So you can actually take the vector field and spin it about this line right here. And you'll get some new vector field. I'll call it, instead of V, I'll call it W for the rest of this video. W of x, y, z. So you got to be careful. I've changed some of my variables so that the axis of symmetry, this vertical axis, is now z, where I used to have a y-axis right here. So these 2 spots where I had singularities, the yellow and the green singularity, this sort of foliates around into a circle. Foliates is the wrong word, but it sort of spins out and covers a circle's worth of, well, I shouldn't orient it. There's no reason to orient it, but a circle's worth of singularity. So this is a circle's worth of singularity in the new vector field of, I should say of, W. Okay. So because that 2D picture that I have has that left-right symmetry, it actually kind of helps me descend to a vector field defined on the 3D space, where I'm zooming in right now. I've got x, y, z, and around each each slice, I should get this sort of rotation about the middle circle. So the vector field truly looks something like this. It's hard to draw vector fields in 3D with keeping precision, but what I've drawn is I've drawn the vector field along the y equals 0 slice. Let me draw it in the x equals 0 slice. I'll do that in blue. I hope this doesn't get crazy, but it's something like this. And over here in the back, it's coming up, around, through like this. So it's sort of, the vector field is sort of foliating, I don't know if foliating is the right word, but sort of what's the word I'm trying to look for? It's sort of spinning around these nested donuts. That's the vector field that we really get, which we're allowed to get from any vector field that exhibits this symmetry up here. So what we have is now a vector field W of X, Y, Z over here, which has a circle's worth of singularity. Basically, if I actually wrote down the formula for W, I would have division by 0 along that red curve, along that red circle in the Z equals 0 plane. Okay, so I would like to somehow provide some sort of argument or explanation for why I would say this vector field is probably still conservative, or at least not conservative, but is curl free. The reason is as follows. So locally, W is the gradient of some function f. Now I need to tell you what that function f is. If you take a point x, y, z, not on the red circle, I need to tell you what the function is. So I'm going to minimize all of this for a second. If you take a point x, y, z that's not on the circle, let's just look from above. This isn't a perfectly rigorous argument, but this is the point as a bird's eye view. What I would like to do is slice, take a line that goes from the origin through my x, y point right here. And now I've got these 3 points, and vertically, this looks like a plane where I have my red point here, my other point here, and some point up here. And the function at that point, x, y, z, so f of x, y, z should be equal to theta 1 plus theta 2, or that's theta 1 and that's theta 2. So I'm leaving lots of details to you, but my argument for why the curl of V is 0 relies on the fact that W is equal to the gradient of F, or this is my F. For functions F defined possibly locally. So this is probably the biggest stretch of this video, is that W is the gradient of F locally, and because curl is a local condition, it's just to check if partial derivatives sort of commute, and we actually see that curl of W is equal to Z everywhere, excluding, of course, the red circle of singularity. That red circle of singularity comes from swirling about the 2 points of singularity here. That's the red point of singularity. Okay, so I just kind of want to spend some time and do some fake computations. So here's my x, y, z space, and I'm really not even going to be parameterizing anything. This is my curve. This is my C, which I'm not going to call it C. this is my uh, collection of singular values. So W is singular, or just not defined. That's what I mean by singular, along this circle. And I want to ask myself, like, okay, what is the value of the work integrals of W around, around different loops? So let me just draw a little curve up here. Here's C. Here's some curve C. That's pretty far away from the red circle. So for example, what is the value of V dot T over C? Well, let's think about Stokes' theorem for a second. Stokes' theorem, I know I could bound that curve up there. So I've got this green curve. I can actually bound it by some surface. So here's some surface. I'm not giving coordinates. I'm not giving explicit descriptions of C or S, but I know just by my picture, if the curve is far away from the red circle, that that C can be sort of bubble wand filled in with a blue surface that doesn't touch the red. So S does not touch the red circle of singularity. So now, for that reason, because the blue does not touch the red, I can employ Stokes' theorem. So Stokes' theorem then says that if I pick my normal to be correctly oriented, so I probably need my normal to come down like this, then Stokes' theorem says that this single integral is a double integral of the surface of curl of V dot n dA. But what was the whole point of the previous page? The whole point was that the curl W is 0 everywhere. And notice how quickly I flip my V's to W's. This should be W everywhere. On the previous page, I argued that this is 0 as long as we're not on the red circle. And we're not on the red circle because of my picture says that the blue stays away from the red. So this is the double integral of 0 dA, so that's 0. So what we've learned is that if your curve C stays far enough away from the red line, the red circle of discontinuity, then that work integral should be 0. However, we should think about what happens when my green curve might come through the red curve right there, like this. Okay, so I'm going to call this, let me go to this next page. I'll do the whole picture. X, Y, Z, my singular circle. And now this is my new curve C. So now I've got a curve C. And unfortunately, fortunately or unfortunately, actually in my opinion, fortunately, there is no way you can fill in this disk without the disk ever getting punctured by the red curve. No matter how you fill it in, this red curve has got to puncture the blue curve. So no matter what, there's no way you can draw a surface S bounding C, which is not pierced by the red curve. This is impossible. You can never find such an S, no matter how you draw it. I mean, like, let me erase some stuff around here. So there's my red curve. Here's my green curve. I mean, if I try to build a bubble wand, even if it kind of comes out to the side, my drawing is going to be total crap, to tell you the truth. No matter what I try to draw, it just got to encompass the red curve somehow. It's got to get pierced by the red. And so no matter what, I can guarantee that you cannot use the argument that the W dot TDS is a double integral of the curl of W n dA over any surface, because no surface like that exists. And you could only write this equation if you had a surface that existed outside of the land of singularity. In fact, it turns out that if that's the curve you draw, then you're going to get, I wonder if you can guess it, you'll get that the integral w dot t over c ds is 2 pi. And in fact, one way you can think about this vector field w, which does this sort of rotation about the red line, is that this vector field w is an operator, and it's taking in the curves that your green curve C, and it's outputting a multiple of 2 pi. So in fact, for any curve C twiddle, w dot tds is going to be equal to some multiple of 2 pi, where this multiple tells you how many times your curve C twiddle loops around the red link, the red curve. So for example, I'll give a couple examples. Let me do this. My final answer, and I'll kind of be done. So here's my curve of singularities. Then if I draw, this is my C, which comes down. It comes down again. Okay, so I've kind of come through that bubble wand twice. In this case, I've come through twice, so my k is 2, and my integral w dot t ds is equal to 4 pi. If I did something like this, where my curve comes down, loops back up, and comes back down, you know, in actuality, I gotta give it orientation. In actuality, I really haven't actually looped around the red at all. You can pull it around. To get something like this. And now we know we're not linking around the red at all, and because we have no linking with the red, that means my k is 0. My integral of w dot t ds is actually equal to 0. So somehow this is recording how many times you've gotten stuck around the red curve. And the reason why I can draw wiggly pictures is because we have something that's curl free. So the difference between a wiggly picture C1 and a wiggly picture C2, literally the difference, the honest to God difference between C1 and C2 is a surface. And as long as those surfaces don't topologically interact with the red circle, then I can use the double integral of S over S of curl W dot N dA is going to equal to the single integral C1 minus the single integral over C2. But I know this is 0, and the full thing is 0, and this equation always tells me C1 is C2, meaning wiggling shapes doesn't change the actual value, which is like a really, really cool thing. That the fact that you have some sort of flexibility when you're doing all this calculus is a big deal. And this is one of the coolest parts of multivariable calculus. And I hope that this video was instructional for at least one person out there. So do with this what you will.